Let's go. Okay, so I've got formal charge of 0 for carbon. Now I'm going to do it for the oxygen atoms. Okay, so formal charge for oxygen, I've got 6 in the free atom. Okay, is everybody all right with that? Group number 6 for oxygen. Minus, how many bonds do I have to the oxygen outer here?
2.
I've got 2 bonds. How many dots do I have?
4.
I've got 4 dots. So I'm going to say 6 minus 2 bonds plus 4 dots. Alright, now that also gives me a formal charge of 0. So 2 for the number of bonds that the oxygen makes, and then 4 for the number of dots that are on the oxygen. So I look at this oxygen, I've got 2 bonds to carbon. So that's 2 bonds minus, or plus also the 4 dots. We'll do the other one. So formal charge for the other oxygen is also the same thing.
So you have to do it for each one?
You got to do it for each one, right? Each atom has a formal charge. Okay, so all the formal charges are 0, and also all the octets are happy, and at that point we can say we are done. Okay. So the final structure then would be final structure would be that structure with C double bonded O to both oxygens. I have a question for you. How come, or why not? This is more of a Chem 107 concept, or not Chem 107, but what if we did what if we did this structure here for carbon dioxide? See, in Chem 107, you'd be like, well, hey, everything has its octet, so isn't that a viable structure? Right? I mean, you might think that. But let's look at the formal charges for all of these atoms. What's the formal charge of this oxygen?
1 plus.
It's actually minus 1. Right? So let's do the formal charge of the left oxygen. This seems rather cumbersome at first, but after doing this for a little while, it'll come fast. Okay, you'll just do it in your head. So for the left oxygen, we have 6 in the free atom, right? Group number 6, minus 1 bond plus 6 dots. And so that would give me a formal charge of minus 1. Is everybody all right with this? Ask me.
Oh, no.
You're-
Scratching.
Oh, okay, I thought you were like, I don't know. I thought it was like Zoolander, like you're about to go on a walk, or or have a formal charge off, or walk off, or I don't know. Right. I'm always on the lookout for the blank stare, like I don't know what you're saying. So group number 6A, oxygen, right? Free atom. 1 bonded. All right, that's this 1 bond to carbon, and then they've got 6 dots. So instead of moving a pair of dots from both oxygens inward, I moved 2 dots from the right oxygen, and I didn't move any dots in from the left. Okay, but the octet rule is happy in this case. But why isn't it the right structure? So here's one reason why. I've got a formal charge of minus 1 now on this oxygen. For carbon, I've got 4 in the free atom, still minus 4 bonds, 0 dots, so that's okay. Okay, formal charge of the right oxygen would be 6 in the free atom, minus 3 bonds, and 2 dots, okay? And that would be a plus 1. So overall, if I add the minus 1, 0, and plus 1, okay, FC total is still equal to an overall charge of 0. But this is not the most stable structure because the formal charges are now not 0 anymore individually. Whereas if I compare it to our correct structure for CO2, alright, these are my formal charges here for the correct structure. Do you see the difference? So this is why you have to take into account formal charge and not just the octet rule. In Chem 107, they lied to you. They said, oh, just worry about the octet rule and you're happy, you're good. Okay, but there are lots of times when the octet rule is satisfied, but the formal charges are not down to 0, or they're not as close to 0 as they can be. Okay. Let's do some more. Okay, so this is just one example of the Lewis structure, right? But you'll do a lot more. Also, if you're doing this in National Chem and if you have any issues inputting structures, just let me know. I've had people tell me, oh, it took me an hour to input one structure, and then I do it, and it's like two minutes or less. So by all means, stop me and just say, hey, can you just show us, use Master Chem. All right. Any questions on carbon dioxide? You should go through this whole process for every structure you do. Don't jump the gun on making double or triple bonds unless you have to. Okay, now here's something new for Lewis structures as well. Have you ever wondered what the structure is for some of the acid names you learned? So like, for example, what's the structure for chloric acid? What's the structure for acetic acid? All right, we talked about all these acid names. All acids are to be considered covalent. So it's not ionic, it's covalent. Acidic hydrogen atoms for oxyacids are placed on oxygen atoms. So let me get back to the word oxyacids. What is an oxyacid? It's an acid where you've got oxygen atoms in the structure, and the acidic hydrogens are attached to the outer oxygen atoms. So for example, sulfuric acid, chloric acid, nitric acid, all these acids that have oxygen in their formula, the acidic hydrogens are on the oxygen atoms, not on the central nitrogen, for example, right, for nitric acid. You cannot place more than one hydrogen atom on a single oxygen atom. Okay, so I'll get to that too. So let's do sulfuric acid. I think you'll dig this. I hope. Okay, so here's H2SO4, ionic or covalent. Which is it? All acids are to be considered covalent. Okay, how many valence electrons are in this atom? Or, excuse me, compound? 32. Yeah, so I've got 2 from the hydrogens, and I've got 6 from the sulfur, and I also have 6 from each of my 4 oxygens. So grand total, I've got 24 plus 8, that gives me 32 total valence electrons. So are we cool right now? Are we cool? Are we cool? I hope so. Okay. Let's put together the framework. So, so for oxyacids, start by putting the non-oxygen atoms in the center, and then put the oxygens outer like you normally would. Oxygens are usually highly electronegative, they usually go outer. But then the hydrogens, you start attaching them to the outer oxygens. So here's the framework for it. So you got sulfur in the center, and you have the 4 oxygens outer, okay? And then, because I know it's sulfuric acid, I'm going to go ahead and attach an acidic hydrogen, only one to each oxygen atom. I can't put both these hydrogens on the same oxygen. That's not possible. Okay. So if I had 3, if it was, say for example, if it was phosphoric acid, H3PO4, I'd have to put a hydrogen on the third. The third hydrogen would have to go here for the third acidic hydrogen. So any questions about this? Just this primary framework. I think this is really where you're gonna. I hope you get excited for this, because before you see this compound, but you're not picturing a molecule. If you can picture the molecule, you can think chemistry, right? And that's really cool. Okay. So with oxyacids, it's always the oxygens are outer, and then you add the hydrogens even outer still. Okay, and that's just the general way that you do oxyacids. Nitric acid, phosphoric acid, acetic acid, all of the oxyanions that had oxygen in them from that polyatomic ion list I gave you from week 2 or week 1. All of those oxyanions, you can add hydrogen ions to those to make acid names, okay, and you can now draw the structure for those acids, okay, and picture molecules. So we have this framework. How many electrons did we use in doing this framework? 2, 4, 6, 8, 10, 12. So we have 20 left. So where do we put those remaining 20? So step 4 says add any remaining electrons to the outer atoms first. Okay, which atoms are outer in this structure? These 2 oxygens, right? By the way, I could have added the hydrogens to these 2 if I'd wanted, or I could have added one to this one. It doesn't matter, okay? Right, I just went for symmetry. I don't know, just my natural inclination, but it could have been any of them. So we add them to the outer oxygens. So adding 6 dots to make the octets around those oxygens. Okay, and now I have 8 left. So where do the other 8 go? They go to the inner atoms, starting with most electronegative first. Okay, so do they go in the oxygens or the inner sulfur? They go in the oxygens because they are more electronegative. So the last 8 go on the inner oxygens. And of course, like in Chem 107, you're trying to make octets. Okay. All right, we're almost there. All right, so let's, what do we have to do now? What do we check? Only after we've got down to 0 here, do we check the octet rule. Okay, so checking the octet rule. So does hydrogen need an octet? Right, so H is already good. What about oxygens? Do they all have their octets? They do. Okay. What about sulfur? It has an octet. We're done, right? But we got to do formal charge now. So this is where it changes from Chem 107. So let's just check the formal charge. Formal charge of both hydrogen atoms. What does that come out to be? Group number 1 minus 1 bond plus 0 lone pairs. Okay, and so that gives us a formal charge of 0 for both hydrogens. What about formal charge for the oxygens? Well, let's do, there's two kinds of oxygens here, right? We got the OH ones and then we have the outer ones. So formal charge of the bonded oxygens with the hydrogen could be 6 minus, how many bonds? 2 bonds and 4 dots. Okay, 2 bonds and 4 dots. So that gives me a formal charge of 0 for those. What about the formal charge for the oxygen outers? Okay, the outer oxygens. 6 in the free atom, okay. Valence electrons are 6, group 6A. How many bonds? 1 bond. How many dots? 6 dots on the outer oxygens. So I've got a -1. What about the sulfur? Group number 6 minus, how many bonds? 4 bonds. How many dots? 0 dots. I have a +2 formal charge. So let's write the formal charges in the structure that we have. So I've got a +2 here on the sulfur. I've got the 0s on these oxygens. 0s are also on the hydrogens. I've got -1s on the outer oxygens. Is there a way that we can get these -1s down to 0 while also at the same time getting the +2 down to 0? Make double bonds, right? So what we're going to do is move in 1 pair of dots inward from both oxygens, and this should do the trick. All right, so we do that. There we go, final structure. So in Chem 107, you'd be like, hey, wait a minute. Sulfur has its octet exceeded. That's not right. But in this class, we're telling you it's okay. That's the way it's supposed to be. Okay. We're finally completing the picture. We're no longer lying to you anymore. Now this is a long process. I broke down all the steps to you. As you get more practice doing these, it goes a lot faster. All right. So any questions on sulfuric acid? We're going to have an entire lab exercise next week on just practicing these. Okay, so we'll grind this out a lot more. All right. All right. Let's do some more. All right, here we go. Determine the Lewis structure for magnesium hydroxide. What's the first step? Is it ionic or covalent? So this is ionic. Okay, how many valence electrons do I have? Well, let's break it up. Let's break up the ions. Right, magnesium 2 plus, OH minus, and another OH minus. So valence electrons for magnesium 2 plus is going to be 0, right? So I get 0 for that. How many valence electrons do I have for hydroxide? I've got 6 from oxygen, plus 1 from hydrogen. What do I do with that minus charge? All right, you're going to do the opposite of logic. Minus means add in this case. Plus add another one. So we're going to total have 8 valence electrons for each hydroxide. Again, why am I adding one when I'm supposed to be subtracting one? Well, what does the negative charge mean on a molecule? It means you have an extra electron. I'm adding an electron to the count to take into account the minus charge. Make sense? So I've got 8 valence electrons there, 0 for the magnesium 2 plus. Again, why is this 0? Well, magnesium had 2, but it lost 2 because now it's got a plus 2 charge. Where did these other 2 electrons go? Well, one went to hydroxide, and the other one went to the other hydroxide. Right? Ionic bonds don't share electrons, they just get transferred. Okay. And then other hydroxide also has 8. So from Chem 107, because they never taught you to look at ionic versus covalent, you would just say, oh yeah, the whole molecule together has 16 valence electrons, and this would be the structure somehow, right? You would say, oh yeah, I got magnesium, and it's covalently bonded to hydroxide. I'll see stuff like this all the time. How does hydrogen make 2 bonds? I don't know. Right, but I'll see this because again, they never were taught this. Okay, if you understand what ionic means, it means you break them up. Okay, so let's do step 3. Okay, so step 3, put together a framework. So our framework is going to be magnesium with its 2 plus charge. It's by itself. It's a monatomic ion. And then you get 2 hydroxide ions. And with the hydroxide, we used up 2 electrons, so we'll have 6 electrons left for each of these. Okay, step 4, add any remaining electrons to the outer atoms. Well, we don't add any to hydroxide, but we do add them to oxygen. So you end up getting magnesium, you can just write a note here. 6 electrons left on each OH negative. Okay, just to be on the succinct side. Okay. So is everybody okay with how I went from this to that? Is everybody okay with how I went from this to this? Okay, just again remember with ionic compounds, you got to break up the ions. Each ion. So when you do an ionic compound, you have a separate Lewis structure for each ion. Okay, so I'm just looking at OH. I'm saying, okay, polyatomic ions. You might remember me saying this from weeks ago. All polyatomic ions are covalent. You remember me saying that? This is another reason why I was saying that. Because we keep the polyatomic ions together. Right? We don't break away the oxygen from the hydrogen. Why? Because hydroxide ion is a covalent compound. But we do break away the magnesium away from the hydroxide because that's the metal that was ionically bonded with the hydroxides. Okay. Can we get rid of, let's look at the octet rule. Okay. Is the octet rule happy for all these atoms? Yes, right? The only atom where we have to worry about the octet rule, in this case, is oxygen. There's 8 around both oxygens, so we're good there. Okay, so we're just going to say octets are happy. What about the formal charge? So if we look at formal charge, alright, so Fc for oxygen is what? -1, right? Each oxygen, you know, in each hydroxide has a -1 formal charge. Again, is everybody okay with that? Anybody need me to show how you got that? Okay, so again, it's 6 in the free atom minus 1 bond plus 6 dots. So 6 minus 7 is -1, right, for oxygen. Hydrogen's formal charge is 0, right? That's just 1 minus 1. Right, magnesium formal charge is 2 plus. That's okay. It's supposed to be 2 plus. So what? Can we do anything else here? I'll tell you, we're done, but there's one extra added feature.
Yeah, just put the charges on the hydroxide.
The charges on the hydroxides, right. So how do we do that? Do you remember how we do that?
Brackets.
Brackets, right, we bracket. Okay, so we're going to go ahead and throw brackets around the hydroxides. Do we need to bracket magnesium? And the answer is we don't, because the whole purpose for brackets is to use them on polyatomic ions that have a charge, you know, that have a collective charge. Now it turns out the formal charge of -1 on the oxygen is the reason for the minus charge in hydroxide. But the way that we do it is we say, well, the polyatomic ion collectively shares that charge. Okay, so because the polyatomic ions, all the atoms collectively share that charge, we bracket the polyatomic ions and put the charge on the outside. Monatomic ions, no need to bracket because the charge specifically belongs only to the atom, so we don't need to worry about that. So final answer would be that.
I'm sorry, could you explain how you got negative?
How I got this -1?
Yeah.
So formal charge of the oxygen, I'll draw it right up here. So Fc oxygen, the group number for oxygen in the periodic table is what? 6. Okay. Is everybody alright with that? You alright with it? Okay. Minus the number of bonds to the oxygen. How many bonds do I have to oxygen here? 1, right? How many dots do I have on the oxygen? 6. So 6 minus 7 is -1. Okay. So I'm taking the group number minus 1 plus 6. That gives me 7. All right. So let's go ahead and skip ammonium hydroxide. We just do that problem solving. There is one last note to this whole Lewis structure thing. and that's called resonance. So,